Okay. Here's a quiz. Here's a graph. We want to sketch a graph of f of x minus 2. Well, if you've done the homework, and most people didn't, a couple of people did the homework. If you didn't do the homework, you're going to have a little bit of a harder time understanding this, but get this and then go do it at the half credit page, but do it because this is central. This is maybe along with rates of change, which is going to be this, two most central concepts in the course. Arguably, somebody else might say, well, 2 of the 5 most, but everybody will say these are really important. So you really want to get this. Okay. Your rules for transformations, which I've led up to a whole lot in my class. Okay. So if you're in my class, you should understand that this shifts everything 2 units in the horizontal direction. So you're going to take this graph and move it over 2 units. So it'll be here. 2 units is that far, right? So you move every point over 2 units. You just move the whole rectangle over 2 units and sketch the same curve. F of x plus 2. All right, these kind of small, and I apologize for that, but shift plus 2 vertically. Okay. That'd be hard to read that too. It says stretch by factor 2 vertically. I tell my class, well, if this is in a window, you're just going to make that window twice as high and draw the same curve. And there are other ways to look at that. So I'm going to go over those. Now here, temperature, you got the temperature at 1 o'clock and at 9 o'clock. Now I drew this, but you might not have been able to see it because it might be a little small from where you're looking at. You're always welcome to come up closer. Okay. Some of you are probably 80, 90 feet away, which is hard to do in a room that's only 30 feet long. Okay. Time goes from 1 o'clock to 9 o'clock. So in hours, we could say, well, here is t equal 1. And here is t equal 9. It's not exactly to scale, but we're going to draw it bigger in a minute, but I'm just showing you quickly what you do. Those are 2 times. You put those on a graph. And t equals 1, t equals 9 correspond to vertical lines because t is your coordinate down here. Then you put your information here. Temperature is 74, temperature is 67. Well, I'm not going to try to, 67 is here, 74 is going to be just a little way above it. If you got to do 67 units here, but t equals 0, big T equals 0 isn't particularly important. So we're just going to say this is part of the t-axis, but we're not showing it. Okay. So I'm going to put big T equals 67 and big T equals 74. Okay. Now, if T is 0, big T is 0 down here, that means this little thing's probably about 65 degrees. but it's not showing, just so we can show the graph in a reasonable window. But the window then goes from t equals 1 to t equals 9, and from t equals 67 to t equals 74. Now let's see how this works out. And I'm going to do the second one first because it's kind of easier. Should be more familiar to most people. So I'm going to make a little bigger graph. I'm going to say t equals 1 here, and t equals 9 here. That's little t. Now, little t and big T are completely different letters. If you're spelling things, well, yeah, maybe there's no significant difference except are you capitalizing properly? Okay, they are the same letter, but they are not the same mathematical symbol. The lowercase and the uppercase are two different symbols. So we have 52 symbols that we can use in the alphabet, and then a bunch of them from the Greek alphabet and all that. And we don't need too much of the Greek alphabet in this course, so we won't talk too much about it, but okay. Now here we've got just the same lines I drew here. Drawing it bigger so I'm sure everybody is able to see it. And up here, big T equals 74. And I'll put Fahrenheit degrees. And I'll put hours, just HR for hours. Because now, as I labeled the graph, T is time in hours, and you can't see that because it's down too low, but remember, I made T equals 1 and T equals 9, or little t is time in hours. Big T is in Fahrenheit, 7467. If I'm just drawing the window, it's very useful to be sure I say what each number means by telling you what the units are, so you don't get confused, okay? You don't have to keep thinking, okay, what was that again? You know, right there it is. That's what this is, and that's what this is. Okay, so now I've got a point here and a point here. And I say we want the slope associated with these 2 points. And that's going to be the slope of the line, straight line that goes from one point to the next. Okay. Well, how do you find the slope? There are formulas, y2 minus y1 divided by x2 minus x1, which isn't difficult to understand. But the thing that you're going to remember longer than you remember y2 minus y1 over x2 minus x1 is rise divided by run. That's what slope is, rise divided by run. And if you remember rise divided by run, and you know to put the 2 points on a graph, is the information here can be represented easily as 2 points on a graph, then we have a run and a rise. Now oh man, hold on. I really screwed up. What's wrong with this? Does this represent the information? Why not? Well, we got the camera running, so you can't say. But show me with your hand what's wrong with this. Okay, tell me the temperature when T equals 1 hour. Does the number, what number does that start? What digit does that start with? What's the first digit? It's 7. It's not 6. I do know the difference between 6 and 7 most mornings. Okay, but I just carelessly drew 2 points here without even comparing it with the information. Okay? Okay, well, you might be prone to doing the same thing. Hopefully not as prone as I am. I've been doing this over 53 years now, teaching it. That's the only second mistake I ever made. In the last 5 minutes. Okay, so here we got the equals 67 degrees and so forth. And 74 degrees goes with 1 o'clock. Now I've got the 74 degrees written right above the 9 o'clock, which is kind of my excuse for doing that, but I didn't read my information carefully and I wrote the information, so I should know. Okay, 1 o'clock, it's 74 degrees and the temperature is going down, which makes sense between 1 p.m. and 9 p.m. So there's the correct point. This is the point that says 74 degrees Fahrenheit at 1 p.m. This point says 67 degrees. I don't have a good place to label that because I want to label some stuff over here. That's what this point tells you. And now, if I do this correctly for a change, we've got a more or less straight line from here to here. We'll pretend it's straight anyway. Okay. Now, again, there's a rise and there's a run. Okay. I recommend that you draw arrows for the rise and the run. Now, it doesn't matter which point you start at to do the arrows, but usually we're going to start at the leftmost point and move to the right. So we start here and we move this way, and then we move this way, and there's a path from this point to this point. If we just follow the arrows, we get from here to here. It would be fine, it would be correct, if not quite as grammatical. And we're not going to worry about the grammar here. If you started here with an arrow up here and then an arrow to the left. But usually we want to think from left to right because that's kind of the positive X direction. Okay? Still, it would not be wrong if you drew the arrows the opposite direction, starting from here and leading you to here. As long as you get the right signs and everything. Okay, well, from here to here, this is called the run. And this thing here is called the rise. The run is 9 minus 1. That's how far it is from 1 to 9. Okay. And to get how far it is from 1 to 9, you subtract 1 from 9. If you've got good visualization, you can visualize that too. Or you can count it on your fingers. But the bottom line is you subtract the one you start at from the one you end at, you get your displacement. It's what we call displacement. Okay. And I'm going to put that in parentheses. And I'm going to put the hours on there. It's 8 hours. The rise, well, we start at 74, we go to 67, right? So that'll be and I got the Fahrenheit degrees on there. I didn't write 9 hours minus 1 hour. I kind of factored the hours out, but it's 9 minus 1. It's got to be in hours because the 9 and the 1 are in hours, right? And this difference has to be in Fahrenheit because the rise are the two temperatures are the 67 and the 74 are in Fahrenheit. So you kind of use a distributive law. If you distribute it through here, you get 9 hours minus 1 hour, which is exactly what you have. Distribute this, you get 74 Fahrenheit minus, 67 Fahrenheit minus 74 Fahrenheit. And of course, that equals -7 Fahrenheit degrees. Okay, so now the slope is rise divided by run, which equals eight hours with all that trouble to write 8 correctly. That's the wrong thing to write because that's not the rise. The rise is -7 Fahrenheit. I'm just going to write F instead of F with the degrees. We understand that that stands for Fahrenheit. Okay? And that's divided by 8 hours. And that equals, well, we could write that out as a fraction. Seven over 8 is 0.875. And it's Fahrenheit over hours, which we read as Fahrenheit per hour. And I put a box around this thing. Okay? Now, if you're not in my class, you don't have to do this. If you're in my class, you have to do this later. Okay? So if you do it in your class, the instructor will know what he or she is seeing. It won't be standard. And maybe your instructor in that class wants you to remember formulas. I don't, we debate some of these pedagogical things, but it's one of those debates is, either way, it's perfectly okay. Because none of us presumes to judge what the other's doing. Everybody's got their own perspective, and we're all competent. Maybe the exception to me, I don't know. Okay, got it? That's how you can visualize and understand slopes and their meanings. Didn't break anything important, did you? Okay. So, makes sense? Now, that is an average rate of change. So also, this is important. I could make it important if I could find my red chalk. I guess that's as close to red as I've got. The average rate of change, because I use capital ROC to stand for rate of change, because it takes a long time to write it out with uncooperative chalk. Okay, the average rate of change of temperature with respect to time, and you're open math just says the average rate of change. It doesn't say temperature with respect to time. I think it's very important to write temperature with respect to time. If you do that, your instructor, if you're not in my class, your instructor will understand it perfectly well because it's very standard mathematical notation that's used all the time. But it's sometimes when it's obvious with respect to what, it gets left off. I don't like to leave it off because it tells you more if you think temperature with respect to time. So in my class, I want you to write it out that way. Not going to determine whether you pass or fail this class. What determines whether you pass or fail this class, remember, is one of two things. If you pass pre-calculus, you pass this class. Okay? If you don't pass pre-calculus, then you're going to need to pass the test in this class, which are much easier than pre-calculus tests with the same foundation. Okay? It just shows me then that if you pass this class and have to take pre-calculus again, you still have the option of taking the support class. But a passing grade in this class tells you that you probably don't really need it. So you're pretty much stamped, okay, go ahead, take the pre-calculus. Without this class, unless you want to repeat this class. Okay? I think it'd make a better grade if you did, but most people don't have time to do that. All right, well, enough digression. Average rate of change of temperature with respect to time is I'll also make the note that's change in big T divided by the change in little t, because your run is the change in your time and the rise is the change in your temperature. Your time goes up by 8 hours, your temperature goes down by 7 degrees. It's a very intuitive idea, just like dividing how much money you make divided by the number of hours you work, dollars per hour. Or how many miles you travel divided by how many hours you traveled, you get miles per hour. There are thousands of important rates of change. And you should probably be pretty familiar with at least a handful or 2 handfuls. Another way of denoting this is delta big T over delta little t. If you have a calculus course in your future, then this is very relevant, very important in the languages because the rate of change, well, we could talk about the instantaneous rate of change. Keep taking the rate of change over tinier and tinier time intervals and think about what's going to happen to the time intervals shrink down to 0. Now, when they hit 0, everything's undefined, but right up to 0, you're going to get a slope. Okay? And this might be in a curve. Your temperature might be kind of like this. It might not be a straight line, temperature versus time, your graph. And that would give you the slope of a tangent line. And that's worth knowing now if you're going to go into calculus. So it's kind of a picture you can carry with you as you look at these graphs. Because that's the first thing you do in calculus is you learn how to calculate instantaneous rates. But it's just an extrapolation of this rate of change. Every rate that you use in calculating the instantaneous rate is one of these. And you don't need to know too much more. Mainly, what I'm saying is this is really important if you're going to learn anything about calculus. Okay. Now let's go back to this graph and how it changes. So I'm going to have to stretch this thing. So I don't want to drop so low. I'm so high. Let's draw it lower. I do draw the middle line here simply because I know that the squaring function is 0 when x is 0. Middle line is the line x equals 0, and that's an important line. It's the y-axis. Line y equals 0 is, of course, the x-axis. So we come down here and we draw the thing symmetric, but I always mess that up unless I have construction lines. Okay. Again, if you're in my class, you know how to do the construction lines. You'd be welcome to do that. Okay. Now, y equals f of x minus 2. Well, that means we shift 2 units to the right. Okay, your rules, I'll write them up here. And this means shift the graph of f of x. Don't have room to write that. That should be implicit. And I'm abbreviating that just as shift k units vertically. And then AF of x is a vertical stretch, and I'm not going to write any more words on vertical stretch because I don't have room, but we'll demonstrate it. Okay, so here we've got it. Now we want to draw graph of f of x minus h. Well, if everything shifts h units horizontally, then x minus 2 goes over to x equals 0, right? So this line goes over to here, and this line goes over to here, and this line has to move over 2 units. Which means we're going to have a vertical line here. And that's going to be x equals what? Well, if we move over 2 units from x equals 2, we get x equals 4. So there's x equals 4. And x equals negative 2. Now, x equals 4 is what we get when we shift this over. So this is going to correspond to the right edge of this graph. So the right edge goes from here to here, and the left edge goes from here to here. So now this becomes the left edge of our new graph, and this becomes the right edge. In other words, this whole square just shifts over 2 units. We're not shifting up or down to get f of x minus 2, the first one. Just continue our y equals 4 line over to here, and our y equals 0 line continues over to here because it's a horizontal shift. Replacing x by x minus h shifts its h units in the horizontal direction. So now we've got a new rectangle, and we can sketch our parabola here. Now, my 2 units here was a little bigger than my 2 units here, so the thing looks a little fatter than it should. It should look exactly like this. And every point of the original graph should be moved over 2 units to give you corresponding point of the new graph. Now, I'm not sure why I drew those things curved, except that's kind of the way you usually draw transformations of the graph. And that'd be a straight horizontal line, shifting everything over 2 units, okay? Okay, well, then what's f of x plus k? F of x plus 2. So let's see. Well, first of all, this is a graph of y equals f of x minus 2. Just trying to decide what colors are going to show up best. If I want to do f of x plus 2, I've got to raise every point 2 units up, which means I've got to take my whole square or rectangle here and raise it up 2 units. That means I'm going to have a square up here. The x lines are not going to change. I'm not drawing my y line where I ought to. Put a water line there eventually. Label those lines. But every point moves up 2 units, meaning the whole square moves up 2 units. Where's 2 units? Well, square is 4 units high. It's going to move up half its height. Does that make sense? So we can always put a line in here. And this line will be right through the center of the square. It'll be the line y equals 2. So the line y equals 0 for our first graph, since we're adding 2 to all the y coordinates, that's what f of x plus 2 does. Every point has to go up 2 units higher. The y equals 4 line then will go up to y equals 6. And now we have a rectangle within which put our x equals 0 here again, in which we can sketch another parabolic curve. So now we got 3 of them. We got the original one, we got one that's 2 units to the right, and then we got one that's 2 units above. And that'll be the curve for y equals f of x plus 2. Okay. Now, if we want to do y equals 2 f of x, I'll write that up here, y equals 2 f of x. That means every y that we get for f of x is going to get doubled, right? So f of x is our original curve. Every y value here is going to have to be doubled. Well, for example, then y equals 4 is going to become y equals 8. Make sense? So y equals 4 becomes y equals 8. So now here's y equals 8. But y equals 0, if you double 0, what do you get? Show me with your fingers. You get 0. So y equals 0 stays where it is. What happens to y equals 2? Becomes what? Y equals what? 4. Doubles. Okay? So we can put some blue lines, dotted lines. And we can sketch a parabola here. Now, if you do the subdivisions, it's going to be easier. But we're going to have this point right here because if you subdivide once, you get to here, subdivide another, you get to here. And if you're not in my class, you don't know what I'm talking about. But you probably don't need to. And then halfway between here and here. So I'm going to have a point right here. I can figure that out. And I'm going to have a point right here. And it's going to flatten out quite a bit. So now I've got a little bit of guidance and maybe I'll be able to draw a decent curve. So this is a graph of y equals 2f of x. And every point has become twice as far from the x-axis. Okay? If I look at a vertical line, first time in nearly 80 years that something has dropped and I failed to catch it. It's just because I'm coward enough that I didn't want to ram my fingers. That's the only reason. There's no other reason. Get that straight. Make sure you understand that. Okay. Now, before I started my raving, what was I going to do? I'm going to draw a red line, a vertical line anywhere, but I'll just draw it, say, right here. Now, how high is the first graph? It's this high, right? That arrow represents the y value of the first graph, the y equals f of x graph, when x equals whatever it equals here. Okay? Looks like a little bigger than 1.2 or whatever. Doesn't matter what it is. If I draw another arrow right on top of that of the same length, I get to the blue graph, right? Every point on the blue graph should be twice as high as the corresponding point on the original graph. Every graph on y equals 2f of x should be twice as high as on the graph of y equals f of x. Okay, just a, it's a little bit confusing diagram. To be clear, let's label the original graph white, y equals f of x. Yellow is y equals f of x minus 2. A little distorted because I got a little fat there. Okay? The orange graph, if that's what the color is, y equals f of x plus 2. Every point is 2 units higher than the f of x graph. Y equals 2f of x, every point is twice as high above the x-axis as on f of x. In a sense, if you draw any vertical line, this point will be twice as high as this point. Any question that makes sense and help you maybe understand what they were telling you in transformations? And if you're in my class, what I've been telling you all along, here and there about transformations. Okay, now transformations, well, my class has a test this week. We're gonna, very predictable problems. We're gonna go through them, but other class doesn't need to know that. I think at least one other class also has a test this week on chapter 2. Anybody in that class? Chapter 1. Yeah. Okay. Yeah, there are 2 people in my roster who are in that class, but I think only one of them's attending. I'm not sure about that. I keep forgetting who's who. But every once in a while, I email the other instructors and say, hey, so-and-so doing all right? Or how's so-and-so doing? Just so I kind of gauge what I do here. All right. Okay. A straight line has the formula y equals f of x equals mx plus b. Now there is the toolkit function, the y equals x function, which is a straight line through the origin slope of 1. Not talking about that because it's too simple. But we might come back and relate it to this. And when I say too simple, when we're doing the toolkit functions, that one's a little overly simple. It doesn't have any interesting characteristics, but it has important characteristics. Anyhow, this means that you multiply x by m. So if you got the y equals x line and you multiply x by m, you go m times as far from the x-axis. And that gives you a slope of m. So m is a slope. Understand what I just said, and I don't necessarily expect you to because of the way I said it, not writing it, but the slope is m, and if x equals 0, y equals b. So now we're going to kind of move away for the time being, but we'll come back to it when we do quadratic equations. Quadratic functions. Okay. Well, if x is 0, y equals b, so we have the point 0b, which we call the y-intercept. Okay. And then we have a slope m. Now, if you have a slope m, this means we can go over whatever number of units. I'll just call that delta x. Then to get a slope of m, we have to go up m times delta x. Straight line goes through these 2 points. Okay? Now I'm going to give you one to work out. Okay? Sketch the graph of y equals 2x plus 3 using what I just showed you. Not going to give you too much time. I'm going to give you a little time to process it. Then we'll look at it because I anticipate some of you will get it, some will get part of it. So we make a little mistake here and there and we'll try to fix that. Okay, wasn't watching the time, we're having too much fun, but this graph, y equals mx plus b, y equals 2x plus 3, m is 2, b is 3. Everybody get that? Okay, so step 1. M equals 2. Step 2. B equals 3. Step 3. Delta x equals 500.
Yeah, great.
Say you can pick anything for delta x. Most of you pick 1 or 2. Yeah, that's fine. Just depends on what scale. Okay. And make the picture. Here's our picture. Say, if b is 3, x equals 500 is overkill. So I'll just use x equals 5. Okay, so here is my y-intercept. That's 0, 3, because this is the line x equals 0. That's the y-intercept. And the y-intercept, or the x-axis is the line y equals 0. Then delta x is 5, so I got to go 5 units here. Okay, let's just say 5 is this far. Okay. Then, but that's our delta x. And our m delta x.
Yes. You got a lot of voice chat.
Over 2 times 5, which is 10. There's our graph. And what's this line? X equals what? Show me with your fingers. X equals. Now my delta x was 5, and I started on line x equals 0. How far is it from here to here? This arrow is 5 units long. It's in the x direction. So x equals 5. And m delta x is 10. So let's see, this is a line y equals 3. So this must be the line y equals 3 plus 10 equals 13. So the coordinates of this point should be 5, 13, and I'm just looking for a good place to write that. Okay, now there's a lot more to do with the equation of a straight line. You're going to need to go to open math to figure that out. But people are having a lot of trouble with this picture, and this picture is really where you need to start for understanding graphs and many other things.